Do many worlds explain quantum probabilities? Imagine flipping a coin and covering it without looking. You know it's either heads or tails, and if it's a fair coin, the odds of each are at 50%. But in the quantum world, things are a bit more intriguing. If this was a quantum coin, before you look, it's in a state of superposition, not definitively heads or tails. In quantum mechanics, the world is described through wave functions, which are like fuzzy clouds of possibilities that evolve over time. For our quantum coin, before you look, its wave function isn't just heads or tails, it's both at the same time. This concept of superposition is crucial in quantum mechanics, but honestly, it's a bit of a head-scratcher. No one fully understands it, but we do know it's essential for accurate predictions in quantum physics. When you finally observe the coin, the superposition collapses into one definite state, either heads or tails. The transition from a superposition to a definite state is known as the measurement problem, and it's a big mystery in physics. To explain this, various interpretations of quantum mechanics have been proposed. The Copenhagen interpretation, for instance, suggests that upon measurement, all but one of the superposition states vanish, leaving only the state we observe. Then there's pilot wave theory, which posits a sort of underlying reality that dictates which state in a superposition is the real one. And then we have the many worlds interpretation. This interpretation tells us that the Schrödinger equation, which governs the evolution of wave functions, is all there is. There's no wave function collapse, no special underlying reality. Instead, all possibilities in a superposition are real and happen in separate, branching worlds. So does many worlds solve the measurement problem? According to this interpretation, we don't see superpositions of macroscopic states, like a cat being both alive and dead, because we are part of the wave function. We exist in a branch where we observe a single outcome, like heads on the coin. Meanwhile, another version of us in another branch observes tails. While compelling, the many worlds interpretation seems impossible to test directly, because we can't interact with these other branches. But there's a twist. If this interpretation can explain other mysterious aspects of quantum mechanics, it gains credibility. Now let's look at the Born rule. This rule helps us determine the probability of a specific outcome when measuring a quantum system. The probability is the square of the wave function's amplitude for that outcome. It's a foundational concept in quantum mechanics, but has always been somewhat of a given, without a deep explanation. Now let's start with a coin, but not just any coin, a quantum coin. In the quantum world, we describe things using wave functions. Imagine a wave function as an arrow pointing in a direction that shows you how much heads-ness or tails-ness our quantum coin has. The strength of each state, heads or tails, is given by coefficients. Let's call them alpha and beta. In the quantum world, the length of our wave function arrow stays the same. Thanks to Pythagoras, we know this length is the sum of the squares of alpha and beta. Typically, we set this length to 1. So if our quantum coin is fair, alpha and beta are both the square root of a half. Now here's where it gets tricky. The Born rule in quantum mechanics says that the chance of our coin landing on heads or tails is the square of its corresponding coefficient. If our coin is fair, both probabilities are a half. You might wonder, why should these coefficients decide the probabilities? That's where the many worlds interpretation comes in. It suggests something pretty wild. Every possible outcome of a quantum event actually happens, but in different parallel universes. And yes, it is as crazy as it sounds. To understand this, let's do an experiment. Imagine flipping the quantum coin and then waiting without seeing the result. The coin, the measuring device, you, and the environment, everything becomes part of a giant wave function. In quantum physics, there's this thing called entanglement. It means that once particles interact, they become linked, and their states depend on each other, no matter how far apart they are. So when our quantum coin is flipped, it becomes entangled with its surroundings, including you. Many worlds says that in this scenario, the universe splits into different branches, one where the coin is heads and another where it's tails. And you, the observer, exist in both branches, but only aware of the result of your respective branch. This interpretation tackles the measurement problem in quantum mechanics, why we see definite outcomes instead of weird quantum superpositions. In the many worlds view, we do see superpositions. They just happen in different branches of the universe. But why do we experience specific probabilities like the Born rule suggests? Well, let's talk about and think about a clone experiment. Suppose you have clones in different cities, let's say LA, New York, and Buenos Aires. Without any other info, each clone has an equal chance of being you. If there were only 2 cities, the chance would be 50-50, but with 3, it's a third each. Back to our quantum coin. If alpha and beta are equal, then each outcome, heads or tails, gets equal probability, just like our clones in 2 cities. That's the Born rule in action. But what if alpha and beta are different, like root, a third, and root, 2/3? Intuitively, you might think the probability should still be 50-50, but according to the Born rule in many worlds, the probabilities are now 1/3 and 2/3. This is where many worlds shines. It suggests that the number of worlds or branches where a particular outcome happens is proportional to the square of its coefficient. So the more a specific outcome weighs in the quantum superposition, the more branches of the universe will reflect that outcome. Now, imagine I deal you 6 cards, one of which is a joker. We divide them into 2 stacks of 3. What's the chance that the joker is in your stack? You'd say 50%, right? This is because you're using something called the principle of indifference. Basically, if I swap the stacks, nothing changes, so the chance of the joker being in your stack is the same as it is being in mine. But what if I take a card from your stack and add it to mine? Now I have 4 cards and you have 2. The odds aren't so straightforward anymore. But here's a trick. If I split my stack in 2, we have 3 stacks of 2 cards each. Swapping these stacks doesn't change the situation, so the joker has an equal chance of being in any stack. Thus, the probability that the joker is in your stack is 1/3. In the many worlds view, every possible outcome of a quantum event is real and happens in its own separate universe. So when we flip a quantum coin, it doesn't just land on heads or tails. Instead, the universe splits into 2, one where it lands heads and another where it lands tails. The big question is, how do we figure out the probabilities of each outcome in these many worlds? This is where our card game analogy comes back into play. The wave function can be a bit like our stack of cards, and we can divide it to understand the probabilities of different outcomes. For example, if we have a quantum coin that's more likely to land tails than heads, we can split the tails outcome into 2 or more to balance the probabilities. This is a bit like splitting my stack of 4 cards into 2 stacks of 2. By doing this, we can apply the principle of indifference to say that each outcome, heads, tails 1, tails 2, has an equal chance of happening. What's fascinating is that by using the principle of indifference in the many worlds interpretation, we can arrive at the Born rule naturally. This means we don't need to add any extra rules or assumptions to our theory. It all comes out of the many worlds interpretation itself. But hold on, can we just split quantum states however we want? Are these split states still valid in quantum physics? Well, remember, we never observe quantum objects directly. We only see their effects on larger, measurable things like our quantum coin affecting a measurement device. So, in theory, we can split these quantum states to balance out their probabilities. You might wonder if this approach is unique to the many worlds interpretation. Can we use it for other theories like Copenhagen or pilot wave theory? Well, parts of it apply to other interpretations. However, the way we use the principle of indifference changes depending on the interpretation. In many worlds, this principle directly helps us understand which world or branch we might find ourselves in. So the next time you flip a coin, remember that in the quantum world, you're not just choosing between heads or tails. You might be branching into multiple universes, each with its own story to tell. Welcome to the fascinating and mind-bending world of quantum physics.